Okay, so the video was cut off while I was writing this problem. I don't know what happened here. Um, okay, so let's take a look. What do we do? So I left you with this problem. What do you notice? The first thing I think you should notice, you should try to compare them to each other. What are they? So 3 plus 3 is 6, 6 plus 3 is 9, 9 plus 3, 12, 12 plus 3 is 15. So you can think about this as like that. But how can you compare it to the first term and the second term and to the nth term? Do you see it? The common is 3. Common factor is 3 in everything here. So this is 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5. Wouldn't that make it a n, 3n? Check it. A1 is 3 times 1, which is 3. A2, 3 times 2, which is 6. A3, 3 times 3, which is 9. A4, 3 times 4, 12. A5, 3 times 5, 15. This is the right end term. Okay? So I want to give you one more. So number 20, please write it down. 5, 8, 11, 14, 17, and so on. Can you find the right sequence? So go ahead, take the time, go ahead and pause the video and try to see what you have here. This might be a little bit hard for you in here. Once I go over something with you, I think you'll be able to find an easy value, an easy not value, easy way to find the sequence. But I'll go ahead and leave this for you. Try to think about it a little bit. How can you figure this out? What would this be equal to? So what do you notice? Well, so the first term is 5. How can you relate the term itself to the number? The second term is 8. So you want to write it down. You want to see what do you have here. The third term is 11. Okay. This is where you have to figure out what is this. So let's see. A1 is 5, A2 is 8, A3 is 11, A4 is 14, A5 is 17. So they are increasing. So if there's going to be any addition or subtraction, have to be an addition. We're going to have to try to relate it to the term itself. So we can think about if you want to use 2 times 1 is 2 plus 3, 4. It will work for the first term, not the second term. So if we can say an is n plus 4. That would work for the first term. So A1 would be 1 plus 4, that's 5. But would A2 work? 2 plus 4, 6? No, that would not work. We can try AN is 2n plus 3. That will give me my first term. So A1 would be 2 times 1 plus 3. So that will give me my first term. Now can I get my second term? So 2 times 2 plus 3, 4 plus 3, that's 7. That won't work, so I'm going to relieve it. The second term is 8. So n plus a number won't work. 2n a number plus a number won't work. We can try later on subtracting. But suppose, let's go ahead and try to see 3n. So the first term, 3 times 1, that's plus 2. Would that work? So A1 is 3 times 1 plus 2, that's 5. So the first term work. 3 times 2 plus 2. 3 times 2, 6 plus 2, 8. Yeah, the second term work. Is that it? 3 times 3, 9. 9 plus 2, 11. That would work. A4, 3 times 4, 12. 12 plus 2, 14. Work, that's it. 3 times 5, 15. 15 plus 2, 17. That's it. This is AN. Okay. You studied from in algebra, what is it? Sorry, in precalculus. I think you went over sequences. I don't know if you recall doing this. So this is really an arithmetic sequence. Do you guys remember that? Arithmetic sequence. An arithmetic sequence, it's AN is A1 plus n minus 1D. D is the differences. A1 is the first term. So AN, you can use the first term, you can add this to it. What's D? D is the difference between the values. So do we have a common difference? 8 minus 5 is 3. 11 minus 8 is 3. 14 minus 11 is 3. 17 minus 4 is 3. So D is 3. And A1 is the first term, that's 5. So this is the nth term right here. Okay? I guess you can think about this as a arithmetic sequence as well. So in this case, the nth term is A1, which is 5, plus n minus 1D, so n minus 1D. Okay, so you can, if you want to, D is what in this case? D is 3. Is 3, so I'll put this here, and that will give me what? 5 plus, distribute the 3, n minus 3. So 5 minus 3 is 2. 3n minus 2, that's the same. Did I? N minus 1. Oh, it's 5 minus 3 is 2, not minus 2. So 3n plus 2. 5 minus 3 is 2. So AN is 3n plus 2. We got this here, but this is a lot easier, didn't we? We recognize it's an arithmetic sequence. You know, the difference between any two consecutive terms is equal to 3. I don't know if you know this, but this is the arithmetic sequence right here. This is the nth term for an arithmetic sequence. D is the difference from any two consecutive term, and A1 is the first term, so you can find the nth term from there. Okay, so this is an example right here. Okay, so here I'm going to give you a definition, intuitive definition of a limit of a sequence. Sorry, across this. If you have a sequence an has a limit L, we can write the limit an as n approaches infinity equal to L, or this. Now, if the limit an exists, we say the sequence converges or is convergent. Otherwise, we say that the sequence diverges. So let's take a look at a problem. So from the book, if you have the book, let's take a look at number 27. In number 27, an equal to 5 over n plus 2. We want to find out if the limit of an as n approaches infinity converges or diverges, exists. If the limit of an as n approaches infinity exists, then the sequence converges. So let's go ahead and do this. Now, if you recall, you've done that in algebra. What do? We divide it by what? The greatest power of the denominator. And what does that give me? That's going to give me 5 over n. N over n is 1 plus 2 over n. Now, if we take the limit of an as n approaches infinity, that's the same as the limit of 5 over n divided by 1 plus 2 over n as n approaches infinity. What is that going to give us? So the limit of 5 over n as n approaches infinity, if you recall, what is that equal to? Some number here, 1 over n as n approaches infinity. This becomes larger and larger, so the limit of 1 over n is 0. So this is 0 over 1 plus 0, which is 0. The limit does exist and it's equal to 0. So what is this? What do we know? The sequence converges. Okay, so this is number 27. Let's go ahead and do number 28. So an is 5 square root of n plus 2. Let's see if this sequence converges or diverges. So let's go ahead and take a look. What do? Well, if an approaches infinity, what do you have? Let's see, the limit of a of n and n approaches infinity is the same as the limit as 5 square root of n plus 2 as n approaches infinity. You can ignore this, but it's going to be, wouldn't that be infinity? So this is infinity. The limit doesn't exist, so this one what diverges as n it gets really large. Okay, the limit is not equal to a number L, so what we have, the limit, the sequence diverges. So let's go ahead and do a few more problems. Number 20, let's take a look at, for instance, let's take a look at number 30. Number 30, we have an is equal 4n squared minus 3n over to n plus 1. What do you have here? So the largest power in the denominator is n, right? So we can divide this by n. You can, and what are you going to have? This is going to give us what? 4n squared over n minus 3n over n we could have done it the way I've done it in number 27, but that's okay. 2n over n plus 1 over n. So these cancel out here, the n together, and this n with this n. So what do you have here? One of the n's here cancel out, so you have 4n minus 3 over 2 plus 1 over n. So what do you have here? an, in this case, approaches what as n approaches infinity? An approaches infinity as n approaches infinity, doesn't it? Okay. Why is this? Because of this. So as n approaches infinity, this is going to be very large, which means an approaches infinity. So basically, it's like taking the limit of 4n minus 1 minus 3 as n approaches infinity. That's equal to what? That's going to give me infinity. And the limit of the denominator, which is 2 plus 1 over n, as n approaches infinity, this goes away, becomes 0, and that's equal to 2. So since we have this, an approaches infinity as n approaches infinity. So the limit of an as n approaches infinity is infinity, it diverges. The sequence diverges. Okay, so this is number 30. We can do more problems. Let's take a look at do more problems. Let's do one with radicals. So let's take a look at number 34. So go ahead, try to do number 34. Let me look at it so I won't write the wrong problem. 3 square root of n plus 2. So go ahead and pause the video and try to do this problem number 34 in section 11.1. Okay, so I'm going to start it now. So the way you think about it here, the largest, here is square root of n. You can divide this by square root of n. So that gives me what? That's giving me 3 over, just cancel each other, 1 plus 2 over square root of n. So what happens as n approaches infinity? As n approaches infinity, what do you have? An approaches what? This is gonna get 0, so 3 over 1. An approaches 3. An approaches 3 as n approaches infinity. Another way of saying it, the limit of an as n approaches infinity is equal to 3. So what do we have here? The sequence converges. Okay, so I'm going to give you one more problem. That's number 42. One with -1. Number 42. So here we have a situation with a negative 1 raised to the n plus 1. If we ignore this for a second, if we just take a look at this for now, what do we have? So if we take the limit of just n over n plus square root of n and see what happens here as n approaches infinity. So divided by the greatest power in the denominator, so this is square root divided by n divided by n divided by n. And what does that give us? So that gives us what? The limit as n approaches infinity, that's 1 over 1. So wouldn't that be the same as 1 over square root of n? So remember here, power 1, this is 1/2, right? So n to the 1/2 here, n1. So 1 over n, 1 minus 1/2 is 1/2, which is square root of n. So as n approaches infinity, this becomes 0, so that's equal to 1. So the limit of this is equal to 1. However, I have negative 1 to the n plus 1. So what does that mean? Well, n plus 1 must be even, so n is odd. So for odd number terms, this would be positive 1. So for odd numbered terms, you see what I did? When n is odd, n plus 1 is even, which make this positive 1. So for odd number terms, an would be positive. Positive what? Positive 1. Okay. So for odd number terms, an approaches 1. Because I just did this, and this is the limit equal to 1. Now for even number terms, if this is 2, 2 plus 1 is 3, it's going to be even. It's going to be, negative. So an is going to be negative 1. Negative 1 times 1 is negative 1. Of course, as n approaches infinity. So what do you have? The sequence an is divergent. Some goes to 1, some approaches negative 1. It's divergent. Now keep in mind, if I get rid of this, if I just have an is equal to n over n plus square root of n, the sequence is convergent. But I have negative 1 to the n plus 1. It's divergent. Okay? So the sequence diverges. All right? So that's what we have here. Some of the problems that we've done. I hope this is enough. We can later on do more problems if you like. So let me go over a couple of theorems here. Well, first, a definition. Let me go over a precise definition of a limit of a sequence. Okay, a sequence an has the limit L, and we write limit of an as n approaches infinity equal to L, or an approaches L as n approaches infinity, if for every epsilon, do you guys remember epsilon from calculus 1? Epsilon greater than 0, there is a corresponding integer n such that if little n greater than n, then absolute value of an minus L is less than epsilon. Do you guys recall that? You went over, you saw that in calculus 1. Okay. All right. So now the theorem, if limit of a function f of x as n approaches infinity is L, and the function fn equal an, then the limit of an as n approaches infinity is equal to L. Okay. Same thing as you've seen it here, visually looking at it. So it's approaching some number L, right? So the sequence, you have 1, 2, 3, so on, all the way to n. So it might go like this, but it approaches the value n3, L, whatever L is. Okay, for each term. Okay. The limit loss for sequence now the first one is the sum law, and I think you've seen something similar to that. Probably not with n approaches infinity though. So this is the sum law. The difference law is a limit as n approaches infinity, an minus bn, that's a limit of an as n approaches infinity, minus the limit of bn as n approaches infinity. And now the constant multiple law. The constant multiple law is the limit of can, where c is a constant. As n approaches infinity, you can pull out the c. That's a limit of an as n approaches infinity. Okay, and for here, the limit, the product law, an bn as n approaches infinity, is the limit of an as n approaches infinity times the limit of bn as n approaches infinity. And the quotient law for 5, the limit of an as n approach over bn as n approaches infinity is the same as the limit of an divided by the limit of bn, provided that the limit bn as n approaches infinity is not 0. So you've seen something similar to that here. Now let's take a look at the power law. The limit of a n to the p as n approaches infinity is the limit of a n as n approaches infinity raised to the p power. Now if p is greater than 0 and a n is greater than 0. Okay, now I want to give you one more here. I want you to take a look at the squeeze theorem for sequence. The squeeze theorem for sequences. Okay. Now if an is less than or equal to bn is less than or equal to cn, all of these are sequences for n greater or equal to n0, and the limit of an is equal to the limit of cn as n approaches infinity equal to L. So limit of an equal to the limit of en equal to some number L, then limit of bn must be also equal to n. Limit of bn as n approaches infinity must be also equal to L. And this is what we call the squeeze theorem. The squeeze theorem. So an example would be, here is an, bn is larger than this is bn, this is cn, this is an, and this would be bn. In between these two, this approaches L, this approaches L, and bn must approaches L as n approaches infinity. This is what we call the squeeze theorem. Okay, let's go. And let me give you this theorem here. The limit, if the limit of absolute value of an as n approaches infinity equal to 0, then the limit of an as n approaches infinity also equal to 0. Okay. So here we have a couple of theorems. If the limit of absolute value of an as n approaches infinity is 0, then the limit of an as n approaches infinity is 0. Now here, if the limit of an as n approaches infinity approaches a value L, and the function is continuous, then the limit of f of an as n approaches infinity is equal to fl. Okay, now here's the one that you should also always consider. If you have a sequence r to the n, so raised to the nth power here, is convergent if r is between -1 and 1, but it's divergent everywhere else. So r would have to be pretty much a fraction, wouldn't it? If you have r that's greater than 1, 2 to the n, and n approaches infinity, obviously you're going to see that it's not going to be convergent. So the limit of r the n is equal to 0 as n approaches infinity, of course, if -1 less than r less than 1, and it's equal to 1 if r is equal to 1 and is divergent everyone else. Okay, so if you have a fraction raised to the nth power, r is 1/2 in this case. This is as n approaches infinity, right? So the denominator becomes very, very large. So this approaches value 0, right? So that's the same as 1/2 to the n, and this approaches infinity, and this is going to be equal to 0. So that's what we have. So when do we have a sequence increasing? A definition here. A sequence is increasing is called increasing. You can see it in the values, right? If an is less than an plus 1, an plus 1 is less than an plus 2, and so on, for all n greater or equal to 1. So a1 would be less than a2, would be less than a3, would be less than a4. Now it's called decreasing if an is greater than an plus 1, and so on. So an greater than an plus 1, a1 is greater than a2, is greater than a3, and so on. Here is opposite. a1 is less than a2, is less than a3. Now a sequence is called monotonic if it's either increasing or decreasing. You've seen me as we were looking at some of the sequences. I ask you, look, it's increasing here. So you're adding, I mentioned it. So the values are increasing and so on. Okay. Now, one more thing I want to give you here, a definition. A sequence an is bounded above if there is a number m such that an less than or equal to m for all n greater or equal to 1. As you can see, it's bounded above. It's bounded below if there's a number bounded below if there is a number n such that, I need to go to another one. Let me finish this here. M is less than or equal to an for all n. You can see it bounded above and bounded below. So above the sequence, it's bounded here, M, and here below the sequence is bounded. If a sequence is bounded below and above, it is called bounded sequence. So if a sequence is bounded above and below, above and below, then it is called a bounded sequence. Keep in mind, it's above and below. It is a bounded sequence. One last one here. Every bounded monotonic sequence is convergent. Remember, monotonic, it's either increasing or decreasing. So let's go ahead and do additional problems. We've done some problems, so let's take a look at, let's do one with ln. So let's take a look at number 44. Number 44. So we'll do more problems here. ln n over ln 2n. Number 44, the question is, determine whether the sequence converges or diverges. Find the limit. If it converges, find the limit. So number 44. So here's the thing. What do we do here? an is ln n over ln 2n. We have to use our knowledge of algebra here to find out if it converges or diverges. If you take a look at the denominator is ln 2 plus ln n. Recall that in algebra? The properties of logarithms. ln 2n is ln 2 plus ln n. Now, if we divide both the numerator and the denominator by ln n, what is that going to give us? So this is 1, and this is ln 2 over ln n, and this is 1. Now, as n approaches infinity, this is going to become 0, isn't it? All right, so you can try it in your calculator. If you take ln 2 divided by ln 1000, for instance, you get 0.1. Eventually, as n approaches infinity, this is going to approach 0. So this is going to become 1 over 0 plus 1 as n approaches infinity. So what does that mean? an approaches 1 as n approaches infinity. So it's converges. It converges, right? The limit of a of n as n approaches infinity is 1. Converges. Converges to what? Converges to 1. Okay. So here, number 62, let's take a look at an negative 3 to the n equal n factorial. Remember from n factorial what this is? It's n times n minus 1 times n minus 2 all the way to 1. How do we know if this is convergent or divergent? Well, what do we have here? it's a little bit, you have to think about doing this. So why don't you take the time here, try to see what we have first here. Okay, I'll give you a minute. Go ahead and start working on this. Okay, so let's take a look. What if we take the absolute value of n? What is the absolute value of an? What is that? That is 3 to the n over n factorial. And that is equal to, what is this? So that's 3 over 1 times 3 over 2 times 3 over 3 times 3 over 4 times 3. So we are multiplying 3 the n times, right? So all the way to what? 3 over n minus 1 times 3 over n. So now I multiply 3, you have 3 to the n time here. So this is 1 times 2 times 3 times n minus 1 times n. So this is slightly harder. We're going to have to use what we just saw, the Squeeze Theorem. This is less than or equal to what? So this is less than or equal to what? We can use 3 times 1 times 3 times 2. If we take these two and this, right, wouldn't this be less than or equal to that? I'm just using 3 terms here. Now for n here greater than 2, if you multiply them, 3 times 3 times 3 is 27. 27 divided by 2n. As n approaches infinity, what is this going to give me? It approaches 0 as n approaches infinity. So this is less than this, and this approaches 0 as n approaches infinity. But what is this? This must be less than a number. One safe bet would be, wouldn't that be 0? 0 is less than this, and this is less than this. So what do you notice here? The limit of this as n approaches infinity is 0, and limit 0 is 0, right? So the limit of absolute value of an as n approaches infinity by the Squeeze Theorem is equal to 0, wouldn't it? Absolute value of an approaches 0 as n approaches infinity using the Squeeze Theorem here. And of course, one of them that I just gave you as well, the theorem that I just gave you, let's see where it is here. The limit of absolute value of an as n approaches infinity is equal to 0, then the limit of an is also equal to 0. So using this theorem, then an approaches 0 as n approaches infinity. So the sequence converges and converges to 0. So we use the Squeeze Theorem and theorem number 6, that's the limit of absolute value of an equals 0, then the limit of an equal to 0. So what does that give us now? The sequence an converges to what value? Converges to 0. So this is a little bit tough to go over. This you have to think about ways to figure out how you can figure out if the sequence converges or diverges. The only Squeeze Theorem definitely worked out. Okay. So sometimes you may have to see what this is equal to So at first I did it with the absolute value of an as this is easier to find out the answer, or if it converges or diverges. So we started with the absolute value of an and we went from there. The key here is to figure out to go from here to there and then make this less than or equal to some value. And then you realize the power here is none other than 3 multiplied by itself n times. So that's a good problem, actually. Hope you like it. Okay. If you need more time, please pause the video. I just want to give you a couple of more problems from this section. If you please read number 64 from the book. So they say, use the graph of the sequence to decide whether the sequence is convergent or divergent. If the sequence is convergent, guess the value of the limit from the graph and then prove your guess. Well, I would like you to go ahead and use your calculator, graph sine n over n. So go ahead, use your graphing calculator and tell me what this is equal to. So the limit, graph sine n over n, and tell me what would this be equal to. It would converge to what value? If you notice, if you go ahead and graph it, and it's going to be here, you have 0. It's going to come down like this. I hope you're able to get that. And this is 0 here. So what does it appear? The sequence converges to what value? So the sequence converges to 0. That's how it appeared from the graph. Now figure it out how we can prove our guess here. An is sine n over n. If you notice, sine n over n could be negative or positive. Let's work with the absolute value and then use the theorem 6. Absolute value of an is equal to the absolute value of sine n over n, which is equal to the absolute value of sine n divided by absolute value of n. This is between 0 and 1, isn't it? Well, sine n between -1 and 1, so it's going to be less than or equal to what? This is going to be less than or equal to 1 over absolute value of n. This is at most 1. Okay? What do you know? The absolute value of an approaches what value as n approaches infinity? Well, an approaches 0 as n approaches infinity. Why? Because the limit of 1 over absolute value of an as n approaches infinity is 0. You have the limit of absolute value of an as n approaches infinity is equal to 0. And by the theorem, it follows that what? That the limit of a of n as n approaches infinity equal to 0. So that proves our guess, isn't it? It's coming down, it's going up, it's coming down, it approaches what? It goes up a little bit higher, a little bit lower, it approaches what value? it approaches 0. Okay, so this is using the graph. So a lot of times you're going to be using, if you notice, the absolute value and Squeeze Theorem. We've used that once, I believe, here. Let's see. We can do one more problem. So let's go ahead and do number 69. 69. In number 69, the problem is an equal to 1 plus times 3 times 5 times to n minus 1 over 2n to the nth power. A little bit tough here, but we can do it. So go ahead and check the graph. If you notice, take a pause for a little bit, check the graph. The graph is going to approach 0. It's going to approach 0. Okay. Immediately this approaches 0. Think about Squeeze theorem here. This must be larger than 0, obviously, right? 0 is less than an. An is what is equal to 2 to the n times, and here you have n times. If you can see that, this is a0, a1, a2, a3, all the way to an. Can you see that? So this is 2n is a factor n times. So if we use what we've done in one of the problems earlier, I think it was number 62, think about it. Here we have 1 over 2n times 3 over 2n times 5 over 2n times that's going to be odd, 7 over 2n and so on, all the way to 2n minus 1 over 2n. So here 2n is a factor n times, right? And this is a0 all the way to an, a1 all the way to an. Sorry, I don't want to confuse you. If you take the numerator here by itself, this is the first term. If you're thinking about this problem, this is the second term, third term, this is the nth term, okay? So if you're thinking about this by itself, this is the nth term. So here you have n term, and 2n is a factor n times. So this is the way you can think about this here. And what do you have? We want to squeeze it. Remember, this is 0 is definitely less than this, which is less than or equal to what? Well, you want this to be possibly 1 over 2n, right? Wouldn't that be less than or equal to 1 over 2n? You can consider them all 1, 1, 1, right? And what do you know about this? 1 over 2n approaches what value as n approaches infinity? It approaches 0, doesn't it? So by the Squeeze theorem, this is approaches 0, this, the limit of this approaches 0, the limit of this as n approaches infinity approaches 0. Then the limit of a of n also approaches 0. So by the Squeeze theorem, our an, we can write it down, converges to what? To 0. And you can see it from the graph. I didn't graph it, but it's going to look like this. gonna get a converges to 0. So this is number 69. I'm gonna stop here and see you next time.